Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look into the idea and we're going to formalize standard deviation and variance of a data set. So let's get started by going to the chalkboard and taking a look at two data sets. Two data sets today. Here we go. So the title today is the standard deviation. The standard deviation. Okay, here we go. I need to give you a data set. So I'm going to call this, we'll call the first one set 1. And we'll call the second one, how about set 2? Pretty creative names. The first set, let's take, this is let's try this. How about the numbers 0, 2, 4, 6, 8, and 10. And then for our next data set, let's try something like, how about this? How about maybe a 5, a 3, a 4, a 5, maybe a 7, and a 6. Now, we're going to do two things with this data. Two things. The first thing I want to do is I want to graph this with a dot plot. So I like a dot plot. If you're not sure where to start, I think a dot plot is a very good way to get a quick idea, a quick visual, to get the mind to thinking of where to go. So let's do that. Let's do a dot plot. Okay, so notice this. This is going to be a little busy, but I think this will work just fine. Let's start it out. Now my first data set here is 0 all the way up to 10. So let's go 0. Let's go right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there we go. Now we're going to label these, at least the evens, 2, 4, 6, 8, 10. Okay, so let's do this. I'm going to call this, I have all these pretty colors. How about we'll call this set 1. We'll also do this in pink as well. Okay, so let's put our pink set 1. So I have a 0. I'm going to put a dot for each value. So I have a 0, 2, 4, 6, 8, and a 10. Okay. Now, let's do this. So let's use this pretty green color. And I'm going to put squares. I know it's a dot plot. Or actually, we'll do these are circles really. We'll do dots. So I'm going to do colored. No, we'll do X's. So set 2 is going to be green. And these are going to be done in X's. And let's do the pink. Our set 1, these were done with pink circles. Now I want to stack them on carefully. I have about a 5. Well, that's right here. So I'll put a 5. I have a 3. What else? 4. So I've got a repeat right there. So you can see both. 4. I have another 5. So I'm going to come up here to make another 5. What else? 7. That's all the way over here. And I have a 6. Now, it wasn't intentionally trying to remove my pink, so we want those pinks just as visible as those greens, as the circles, as the X's. There we are. Now, let's look at the data first, before we do anything more. Look at the pink data. The pink data has a minimum here of 0 and a maximum way out here at 10. The green, though, the green has a minimum of 3, but the maximum is only 7. So when you look at the data, the obvious thing to see is that the pink data, the set 1 is clearly just has a bigger range. It has a bigger spread of the data. And that spread is what I'm kind of curious about. But before we do anything more, let's find one of our statistics. Let's take a look at the mean of both data sets. So let's find the mean for set 1 and the mean for set 2. So I'm going to come over here. So the mean X bar for data set 1 is 0 plus 2 plus 4 plus 6 plus 8 plus 10 divided by the number of data. I have 1, 2, 3, 4, 5. I have 6 data. Okay? This is kind of a fun one to add up, because notice I have 10s. There's a 10 plus 10 more plus 10 more. That's 30. So let's write this as 30. Divide that by 6, we can see that the mean for data set 1 is 5. Now, let's repeat that for data set 2. So data set 2, we're going to call it X bar, but this time it's for 2. So we have a 5. Let me write these out in order. I have a 5. Actually, let's use these. We have them ordered on the dot plot as well. That, I think, is easier. So let's use the 3, a 4, 5, 5, 6, 7. Let's do that. Okay. So we have a 3 plus a 4 plus, then we have 2 5s, so 5 plus another 5 plus a 6 plus a 7. And again, we have 6 data values. So let's add, look at this. I see a 10. Oh, there's another one and another one. That's 3 10s. That's 30. Wait a minute. We already said that 30 over 6, that's 5. So what did we just find? These two data sets have the exact same mean. So if you knew nothing about these data sets other than you were told that set 1 has a mean of 5 and set 2 has a mean of 5, then as far as the best you would know about this data set is that it's the same. But let's just put a little concern in there, and I want you to be pondering this. What if these were your job offers in monthly salary when you first finished your job? So job 1 had an average of $5,000 a month. That's what this would tell us. However, when you start job 1, you may get a salary of $0 a month, $2,000, $4,000, or even $10,000 a month if you go with company 1. If you go with company 2, though, the worst you could do is $3,000 a month. The best you could do is $7,000 a month. So, but if all you have is the mean, you don't know that. However, So it's kind of a random guess. So the question then is there some more information that we could provide that without knowing all of the data? And the answer is yes. The answer is look at the spread. The data set 1 has this huge spread. Data set 2 has very little spread. It's all very close to the mean, and that's what we're going to measure. So let's do that. We say that the standard deviation now that is a long word to write, or 2 words to write out. So when we're going to use this in context, so often I'm just going to abbreviate it as SD for standard deviation. The standard deviation is a measure, is a measure of the average let's do this. Is a measure of the spread of the data. Of the spread, the measure of the spread of the data. Now, I'm going to give you a bit of a sentence that's a bit of a mouthful. No, a full sentence that is a bit of a mouthful. It is standard deviation is the average of, I'm going to come back up here, need some more board space, and I'm going to stop there for a moment just to check that my camera is working. Standard deviation is the average of the square of the distance distances from the mean. From the mean. Okay, now I'm pausing because there's actually a little bit more in there. It's really, I should put spread. I'm going to call it spread. Spread is the average of the square of the distances from the mean. Okay, that's what we want to start with, spread. And we're going to just call it SP to get started. So let's try this. So what is our spread? All right, well, let's start, I'm going to call it SP1, because we're going to work on the first data set. And let's measure it this way. Well, we know it's an average, and that it's a distance from the mean. So let's take data set 1 with these values, and let's measure the distance from the mean. So the first data value is 0, has a distance from the mean of 5, plus. Let's take the next distance. Well, the next value is 2, so 2 minus 5, that would be the distance from the mean, plus 4 minus 5, plus 6 minus 5 plus 8 minus 5 plus 10 minus 5. Now, these are all the distances from the mean. And we want the average. There's 6, so let's divide that by 6. Now, I want to be very careful here because there's a point to be made. Notice that when I took each one of these, I took the data value x, like here's x1, and I subtracted the mean. And I was very careful to do that every single time in that order. The data value minus the mean. So what does that mean? Well, this is minus 5 plus minus 3 plus minus 1 plus, here we have a 1 plus a 3 plus a 5. Divided by 6. Now, before you rush to the answer, we need to look at what we just found. These really are what we call, these are called deviations. Deviations are signed distances from the mean. Signed distances from the mean. In other words, 0 is 5 units to the left of the mean. 2 is 3 units to the left of the mean. That's what the negative sign is. It says it moves to the left. 4 is 1 unit left of the mean. 6 is 1 unit to the right of the mean. 8, 3 units to the right, and 10, 5 units to the right. So these deviations represent that some of the values are to the left of the mean and some of the values are to the right of the mean. Well, watch what happens when we add these. Notice that this is minus 5, but here's a positive 5. Minus 3, here's a positive 3. Minus 1, there's a positive 1. This is 0. 0 over 6 is 0. But that can't be because we can see in the data set that there is some kind of measurable spread around the mean. So we have a correction. So correction to measure spread. To measure spread. And I'm going to say why. Because the sum of the deviations is always 0. Okay? So here's the correction. The correction is square each deviation. That's our correction. So let's note that. Correction is to square each deviation. Okay, I'm going to just pause right there for a moment. I'm going to check my camera. Now let's compute our corrective spread. So let's keep going. I'm going to call this the spread for set 1. Now let's take it as the square of each of those. So I'm going to write it out. That would be 0 minus 5 squared plus 2 minus 5 squared plus 4 minus 5 squared plus 6 minus 5 squared plus 8 minus 5 squared plus 10 minus 5 squared. Take all of those. We're going to still average these. Now, let's come back and look at what we just did. I just rewrote this line here. I just rewrote this line, but I squared each one of them so that what happens when you take a negative 5 and you square it, the negative goes away. You take a negative 3 and square it, that becomes a positive result. Whenever you square a number, all of these become positive. So now the deviations aren't going to sum to 0. That's why it's over here we said it's the average of the square of the deviations. All right, here are the distances. So here we go. If we take negative 5 and square it, we get 25. Plus, if we take negative 3 and square it, we get a 9. Plus, if we take negative 1 and square it, we get 1. 1 squared is 1. 3 squared is 9. 5 squared is 25. We're going to take all of that, divide it by 6, and let's see what we get. That's 50, 60, 70. 70 over 6. 70 over 6. Now, there's a few things I need to tell you. Let me just make sure I do this in the right order. Okay. So what I've calculated here is kind of a strange number. And not only that, but this is really what I calculated here is kind of what's called population variance. And even that is arguable for a reason I'm going to show you in a moment. Okay, so this is the population variance. And not only that, it's represented by the symbol of the lowercase sigma. So this is, we looked at the capital one. This is lowercase sigma. The Greek letter, lowercase sigma. And we put a square on it. When we're talking about variance, it's going to be squared. And in general, the formula for the population variance is this. It's the sum of the data minus mu squared divided by n, the number of data. And I'm going to address something here in a moment. We do this because this is the most natural way to think about and measure the distance. However, there's going to be some corrections that need to be made. The first one is this. The first one is we didn't have mu. We don't know all of this is a parameter. But we calculated from a data set. In other words, a sample. So really what we use is x bar. This is, mu is a parameter we used a statistic, difference between a population and a sample. So we're a bit off there. Okay, now there's something else that's not so immediate. Variance is natural to calculate in the way we did here. However, there's something in here that's not obvious. And that is this. When you take a number and you square it, think if those units think if they're dollars. If those units are dollars and you square them, then this answer is dollars squared? What does that mean? What if those units were days? Days squared? Does that make any sense? The answer is no. So to correct our units, to talk about our data with this measuring the spread in the same units as the data, what we have to do is we take the square root of the variance, so now our units match. So let's do this. So what we would say is we would say that SD, I'm going to use that carefully, the standard deviation is the square root of the variance. And so we would just write sigma. And this is the population. This is the population variance. That's the population variance. Okay, now we're going to make a few more corrections to that. But let's proceed with measuring the population variance, or as we're calling it, the spread, for data set 2. We can see that the spread is different. Let's actually check the measure. So let's do this, but for 2. So spread 2. Spread 2, that looks odd. Let me get my eraser. So spread 2 is, we take our data, 3 minus 5, and we square it, plus 4 minus 5 squared, plus 5 minus 5 squared, plus, I'm using the second data set, and I'm taking them in order. I'm taking them from the X's on the original data set, and I'm going to turn the camera so you can refer back to that. Okay, now let's keep going. So our next data is another 5 minus a 5, let's square that, plus 6 minus a 5, square that, plus, this is going to be a 7 minus a 5 squared. And take all of that, divide it by 6, and this is 3 minus 5, that's negative 2, but we square it to get 4. Plus, 4 minus 5 is negative 1, we square it to get 1. Plus, 5 minus 5 is 0, square it, it's still 0. Plus, 5 minus 5 is another 0, kind of got bunched up there. Plus, 6 minus 5 is 1, square it for 1. Plus, 7 minus 5 is 2, square it for 4. I'm going to take all of that, add it up, and again divide by 6 for our average. Well, this is 5 and 5, that's just 10/6. Now, clearly, look at this. 10/6 is clearly less than 7.6. If you're wondering how, oops, this is for 1. So you can see that the numbers, notice that 10.6, this is only 1/7, meaning that the variation in data set 1 is 7 times greater than the variation in data set 2. So 7 times something, that's really big. So when you look at this, the numbers that we're calculating do in fact match with what you would expect them to be. And then if we were to come over here, if we were to take and write let's write the square root of our spread for data set 2. This is the square root of 10/6 is, and let me check, I actually have this written down somewhere, 3. This is about 1.3. And remember, I'm rounding to tenths. My data is in whole numbers, so I round to 1 more decimal. And the square root of the spread for data set 1 worked out to be 3.4. So the standard deviation, as we measure it, is a little bit less than 3 times larger for data set 1, sorry. Now, here's my final correction. Normally, we would call this what's S. And S stands for sample standard deviation. So this is S2, because it's the sample standard deviation for data set 2, and this is S1. It's the sample standard deviation for set 1. Now, here's the final corrections. We say that if we take the sample standard deviation and we square it, we call this sample variance. And it equals probably what you would almost what you would expect. It equals the sum of the data minus, now here's the clever part, this is what we use, the sample mean minus the sample mean, and you square it, which this is exactly what we've done. And then we divide it by, now here's the catch that's, and I don't think at all intuitive, and that is you don't divide it by n. You divide the sample variance by n minus 1. N minus 1. And this n minus 1 has a name. It's called degrees of freedom. And it's also often abbreviated as D.F. degrees of freedom. And where it actually comes from is what's called Bessel's correction. It's called Bessel's correction. And the mathematics of it is actually a bit more advanced than what we're going to do in this course, but just an awareness of it I think is nice to have. And so then we say that the sample standard deviation, S is the square root of the sample variance. So if you were doing your homework and you came to finding the sample standard deviation of the data set, you wouldn't actually calculate the numbers that we did. I did this to show you the idea. your final calculation, so S1 would be 70 over, not 6, or S1 squared would be 70 over 6 minus 1. Well, that's 70 over 5. And, well, 70 divided by 5 goes once, 20, 14. Oh, 14. And S2 squared would have been 10 over 6 minus 1. Well, that's 10 divided by 5. That's going to be 2. And again, you can see that this is 7 times larger than that. So your sample standard deviation, S1, is the square root of 14. And your sample standard deviation for data set 2 is the square root of 2. I know that was a long explanation, but I hope you realize now where the formula comes from, what it's trying to accomplish, and how we have to correct it to be able to use it for our sample data. Thanks for watching.